Yes, good morning, and this is Dan Davidson. I work with the Illinois Soybean Association, and on behalf of the association, I want to thank you for coming in and listening to Dr. Simmons' second webinar titled A Short Review of the 4R Performance Tips. Just a few points before we get kicked off here. This webinar is being recorded, and we did apply for a single CEU, but it could be as much as 1.5 CEUs, depending on how long the webinar goes today. If you registered today to participate in this webinar, you submitted your CCA number, and that will be submitted. If you come back online later and listen to the recorded version of this webinar, either this week or before the August event, testing event, you can always self-apply for a CEU. So the logistics will kick off here shortly. I will introduce Dr. Simmons. He will go through his presentation. You can, with your panel to the right of your screen, you can submit questions, and we'll compile those questions, and then Dr. Simmons will go through them at the end of his presentation. Dr. Simmons, as you know, he gave a presentation at the IFCA event. It's about 2 weeks ago. He did the first webinar last Thursday on fertilizer manure calculations. Today's doing one to review the 4R performance objectives in preparation for the exam. Dr. Simmons is a emeritus professor of soil and water management in the College of Agriculture, University of Illinois. While he's retired from that officialdom over at the university, he still continues to teach courses there, introductory courses in agronomy and soils. He has a long history here working in Illinois on things related to soil and water, soil and water, fertilizer, herbicide fate. So without further ado, again, the webinar will last probably about an hour or so, maybe an hour and 10 minutes, whatever it takes for Dr. Simmons to get through the presentation, and then we'll take questions, and we'll end probably no later than 11:30 this morning. Without further ado, again, on behalf of the Illinois Soybean Association, thank you for coming on today to listen to this webinar. And Dr. Simmons, you have the platform now.
Thanks a lot, Dan. Appreciate that, and welcome everybody. We've got a fun-filled hour plus ahead of us as we go through some of these different objectives. As Dan explained, I'm an emeritus professor, which means I pretty much come and go as I please and don't have to attend any meetings. It's quite a delightful existence. Okay, we're going to talk about the 4 R's, and really my main objective today is to go through these in context and try to prepare you for the exam. So we're going to talk about right source, right rate or amount, right time, and right place for some of the fertilizers that we use in production agriculture. So this is really especially set up for what I call inspired test takers. You have an opportunity on Friday to demonstrate your knowledge in Springfield, those of you that are taking the exam. And as I tell my students in introductory crop science, this exam is an opportunity for you to glorify yourself, your ancestors, and my teaching. So I hope that that is a message you'll keep in your mind as you take this test. So what I'm going to do today is try to focus on some of the key points. Again, as a disclaimer, I have not written any questions for this exam. I've not seen the exam. So my goal is really to try to look at all of the different potential scenarios and try to piece together some things that I might ask, for instance, if I was writing the exam. So really what we're talking about here is looking at scenarios, and I'll make this point at the end of the presentation as well. But I have highly placed sources have told me that there are 5 different cropping scenarios with about 10 questions associated with each scenario. So you really have to go through this systematically using the facts and knowledge that you've accrued as a CCA to try to get these management scenarios down correctly. Okay, just briefly, the roles and responsibilities. A CCA can have a role in planning, and if you look down at the 590 nutrient practice standard, and I've actually poured through quite a bit of literature that's background literature to prepare for this exam, and you can Google in the 590 Illinois Guide. It's an NRCS publication from about 2002, and there's a lot of nuggets on there that I've tried to summarize. But for those of you that want to do more study or more reading, that's a nice thing to look at. And it also references other bulletins and so forth that you can get additional information on manure, cover crops, etc. So really, the CCAs can do 590 plans. They need to be reviewed and sort of approved by the NRCS state conservationists to do this. And the approach of the plan is to include erosion, runoff, and water management practices, as well as adjusting soil fertility through use of manures, fertilizers, and cover crops. Big thing you need to do is to know about N, P, and K budgets from all sources. So this is a recurring theme, and same kind of principles that I've taught in introductory soil science and introductory crop science here at the University of Illinois. There's a method of going through and approaching each one of those scenarios that ensures that you take credit for all the potential nutrient sources. And I'm going to hammer this theme through the next hour. But for instance, if you're using DAP or MAP in the fall, you've got to take credit for that nitrogen against your total nitrogen need. If you're using starter, same thing. So we have to look at all the different sources that we have and account for them. And then finally what we do is we finish off any additional need with our commercial fertilizers. You need to always operate with what's called a realistic yield goal. And that's, some of the literature I've seen says you can add 5 or maybe even 10% on your 5-year moving average to account for increasing genetic potential in some of the crops that we're planting. There's another way this can be done. In the absence of 5-year average data, you can look at some of these bulletins that discuss soil productivity. So another caveat about this exam, the way I understand it, you don't need to bring in with you the knowledge of what the actual yield potential of a Drummer, Flanagan, Sisney, Hoylton are. But you might be required or asked to look at a productivity index or some yield data to try to determine these particular values. So if you've had a 5-year moving average of yield, you might want to look at that and maybe discount an unusually bad year with a drought and then calculate from those numbers. But the yield goals are going to be very important because that is going to really determine, in virtually all cases, the amount of P and K we need in conjunction with our soil test, and to some degree, our nitrogen application, depending on what method is used. So the 590 plan is going to account for all the different nutrients. If you have manure involved, and it's almost guaranteed you will have a question or two that involves putting manure, land applying manure. So you've got to figure out how to do that. You need to look at the sensitivity of each of the soils. You might, for instance, be given a problem where you've got a farm that includes rolling ground and no-till, maybe a little sand pocket in an area that was by a river, some flat black ground, all these different things. You need to know or be able to sort of ascertain what the leaching potential is and the runoff potential is on those particular agronomic settings. There are manure setbacks, so you might, if you have a manure application problem, they might indicate that there's a stream or a sinkhole or something associated with one of your fields, and you're going to have to move the manure application away from those sensitive areas. The 590 plans love the land-grant universities, and the one in Illinois refers repeatedly to the Illinois Agronomy Handbook. Okay, let's talk about soil testing. So for the most part, the main sort of tenets of a soil test would include pH, P, and K. Now we do test for other elements. The reliability of those tests is oftentimes less than 50%. So this is the main building block of a soil test that we will operate from. Keep in mind that pH is going to tell us a lot about nutrient availability. It's going to direct us into what type of phosphorus extraction method we're going to use. It's going to tell us a lot of things. It may tell us something about availability or not of micronutrients. So that's why that's such an important piece of information. And I should add at this point that the water-based pH measurement is the most reliable measurement that we can take on a soil test. You may be asked to calculate a cation exchange capacity. Sometimes this soils data is available for some of our modern soil surveys, but in the absence of any knowledge, you can take 0.6, multiply that by the percent of clay that's in the soil, and go forward from there. And then you can add 2% or 2 times the amount of organic matter. That should actually be a plus sign there. So for example, if you have 20% clay and 2% organic matter, you multiply 20 by 0.6 and get 12, and you multiply 2% by 2 and get 4, and that adds up to 16 milliequivalents per 100 gram of soil. Milliequivalents are a charge unit, which means from that you could tell a distribution of cations, how many of them could be held on that soil. If you're asked to do organic matter, that can be estimated with colored chips. These were made years and years ago here at the University of Illinois. Moist soil, you compare it with colors and you can estimate the amount of organic matter. Why might you want to do that? Well, to calculate the CEC or estimate it would be one reason. And also, it's going to be a guide for getting you into small grains and fertilization amounts. We can't really emphasize this particular diagram too much. I went over this in my other webinar. I went over it at the IFCA conference as well. But this really includes a lot of the sort of philosophy and approach to soil test levels and what sort of action item must be taken. So if you look at everything to the left of the critical level, you see build-up soil above that. You also see on the left axis fertilizer rate, and what this means, if you have a low soil test or very low soil test, that is where you're most likely to get a response to fertilizer. If you are below the critical level, your fertilizer amount for P and K will include 2 components, a build-up component and a maintenance component. And some of the practice problems that I sent out with my handout with the first webinar, you're given one of these problems, and last night, for most of you should have received a sheet that actually shows the solutions. So in other words, if we have a P or K level that's below the critical level, we are going to want to try to increase the soil test level over time, over a period of 4 years. And there's an approach to do that. It's 9 pounds of P2O5 to try to raise the soil test level 1 pound. And this is done over 4 years. So you divide that total amount by 4, and that's your annual addition. So if you're in that build-up soil range below the critical level, you also want to include a maintenance amount of fertilizer, which is going to be calculated by taking the expected yield, that yield average we just talked about, and multiplying that by a factor, okay? And they will hopefully give you that factor, but I've got some examples out of the agronomy handbook on that handout that I put out. So that's what you do to the left of the critical level. In the maintenance range, you are simply fertilizing for the expected amounts of P and K that are going to be taken off that field by crops. I also included in that sheet a biennial application calculation, meaning that you come in one time ahead of corn and you don't fertilize ahead of soybean. So you have to account for the total amount that the corn and soybean might take off and put that in the soil the first year. If you are to the right of the maintenance limit, you are at a point where you have sufficient P or K, whatever elements you're looking at, you have sufficient amounts to actually produce that crop, and you need to be in drawdown mode where you don't want to apply any fertilizer. You actually want to lower that soil test back down into that maintenance range. Here are sort of the parameters for soil testing. You want to do it at least every 4 years. An important caveat here too, if you are applying manure or biosolids, you want to wait 9 to 12 months for that situation to stabilize so that the organic matter breaks down into humus and has a chance to do some mineralization. You may want to do plant tissue analysis for some of the secondary or micronutrients, particularly those that are not really effectively measured with a soil test. In addition, forages is another key area to use plant tissue analysis. So those are the main breakdown of the different types of testing methods you might want to use. Okay, for testing on phosphorus, I think there's a chance you might have to employ this particular piece of information or knowledge, and it's kind of detailed, but we'll go through this. For most of Illinois, our soils are naturally going to be below a pH of 7.3. Okay, So if we go out to the western Minnesota, Nebraska, get into some of the higher pH soils, they may be above 7.3. We'll talk about those in just a second. So for soils with pH less than 7.3, the phosphorus extraction method is known as the Bray P1 extraction method, developed by Dr. Roger Bray and Toby Kurtz here at the University of Illinois in about 1945. Small plug there for the U of I. Okay. Again, the soils that have high pH above 7.3, there's another extraction which uses sodium bicarbonate, which is called the Olsen test. Now, there's a third one developed in North Carolina, NC State being one of your premier agronomy schools. Malic 3, developed by this individual. It's close to the Bray P1 in soils less than 7.3, and it can be used in instead of Olsen, in high pH soils if a colorimetric analysis is used instead of the ion-coupled plasma approach. So that's a lot of detail, but basically for most of Illinois, you use the Bray P1 or in some instances the Malic. P application, again, if we're trying to build up the soil test, we're going to use 9 pounds P2O5 for each pound of soil test we want to increase, and we're going to spread that over 4 years. So let's say we come up with a situation where we need 40 pounds of P2O5 over 4 years, we would then divide that by 4 and get 10 pounds per year, for instance. And you get the maintenance rate from tables when you're adding that if you're to the left of the critical level. Wheat and small grains have a higher need for phosphorus. And the reason for this is phosphorus is important early in their growth, and they've got limited root growth in the fall since they're oftentimes fall planted. So this, and in this case, this is accounted for in some of the tables that we see with the maintenance amount that these would take off. In Illinois, specifically, you have these upper levels that you don't want to put any phosphorus on the soil if you're above 60 pounds per acre on a soil that has a high subsoil P, and there's a map available, or you might get information on where those areas might be. 65 for medium subsoil supply, and 70 for lower subsoil supplying soils. Potassium is tested for with ammonium acetate. Ammonium acetate extraction is used for a lot of cations. The ammonium ion is put into a solution in excess, and that pushes everything off the cation exchange sites, and then potassium can be measured in the extract. The Malic 3 is also acceptable for potassium. Potassium has got an important issue with time of sampling, and this has been studied by a number of people throughout the years. But you want to sample the soil in late summer or fall because there's a seasonal effect on availability. In January and February, the soils are moist. There's more. You basically would get an elevated test. So you want to sample in summer, fall for potassium. pH and phosphorus, by the way, are not affected by seasonality, but you can take that soil sample all at the same time and save yourself a trip. When we're trying to build up potassium in the soil, we use 4 pounds K2O for a 1 pound increase. Remember, phosphorus is 9 pounds P2O5 for a 1 pound increase. Okay, nutrient application timing. This is sort of some philosophy of what we're looking at and what a general approach might be. You want to, if you can, get the nutrient application timing to match the uptake characteristics of the plant. So, for instance, corn takes up about 10% of its total nitrogen load between planting and V6, and then there's a very rapid uptake period. So, if possible, it would be a best idea to come in and side dress that corn, dribble, do something to get that source on at that time. But within that, you've got cropping system limitations, weather and climate, and field accessibility. So, the people that write the test are cognizant that not everybody has the ability, based on some of these factors, to do this, timing as closely as possible to uptake. So, the source. Plant available forms is what we want, and of course all of our commercial fertilizers are ionic forms that are basically ready for uptake fairly quickly. You want to match the source to physical and chemical properties. So, for instance, if you've got saturated soils, let's say you're growing rice, you don't want to put any nitrate form in because that would be subject to denitrification. And here's another key one. I bet you'll, well, there's a likelihood you could see something like this. Urea is a little bit dangerous, as is manure on high pH soils, because we get ammonia volatilization. The hydroxyl, which is the base ion, comes in and pulls a hydrogen off ammonium and then releases it as ammonia. And there's some synergies. P interferes with zinc nutrition in some cases, and in some cases nitrogen can increase phosphorus uptake. All right, let's talk a little bit about nitrogen and its various forms. Of course, we know that there's environmental sensitivity with eutrophication. This is especially important, Lake Erie, the Chesapeake Bay, areas like that have problems with algae. Here are the major nitrogen fertilizer forms that we have. And what I'd like you to do in preparation for the exam is to sort of associate each one of these with a thought process. So you see anhydrous ammonia, what are you thinking about? Application timing. Do we need a nitrification inhibitor? Urea, which also is in UAN solutions. Potential volatilization from the surface based on the work of the urease enzyme, and potential need for a urease enzyme inhibitor. Ammonium nitrate, you've got the two forms there, but the availability is down because of its explosive nature. Ammonium sulfate might have some application for rice, for instance, because it's not in the nitrate form and it stays in the ammonium form if it goes into anaerobic conditions. So here are some things with fall anhydrous we need to keep in mind. And I'll show you some stuff I refer to as the holy grail that you're going to really want to have the command of these particular boxes or matrices. So, for instance, fall anhydrous, if you drop below 60 degrees Fahrenheit, at the 4-inch depth of soil, you can go ahead and inject with a nitrification inhibitor. At 50, you can go without a nitrification inhibitor. But you never want to be before these times throughout Illinois. Not recommended south of Illinois Route 16, which goes down through a lot of beautiful towns and hamlets, but it's for those that go on 57, it's somewhere near Shelbyville. You're dropping down into the Illinois till plain. Fall anhydrous, again, the stabilizer, same kind of thing. You also want soil conditions that favor closing the slot. So extremely wet soils are a bad idea, and extremely dry soils may be a bad idea. You want the kind of moisture there. And the big concern, of course, for fall anhydrous is the concern for nitrification before its time. If we get a nitrification happening, producing the nitrate form, that is going to be vulnerable to leaching or denitrification later on. Okay. So here's the Holy Grail. These are concepts pulled out of this 590 plan, specific bullet points, and I've summarized these down to the ones that I think will really be key for you as you take this exam. Split nitrogen applications are a good idea if you can do it to coincide with uptake. Use your nitrification inhibitors where needed. Again, fall anhydrous would be a key thing on that. And I believe the matrix that they show even suggests that nitrification inhibitors with a spring application may lower some of the potential of loss, particularly on sandier soils. Avoid winter applications. Be aware of volatilization from manure and urea. And two ways to combat this would be to incorporate the urease or manure, or use a urease enzyme inhibitor with that application. You need to remember setbacks from sinkholes, wells, and surface tile inlets, because material can wash over the surface of the land and get into those tiles and then out into surface water again. And if you're in an area with a lot of humanity, you've got to maintain a good practice that keeps odor for manure down. Impact of tillage system. When we start talking about manure and phosphorus, this is going to be kind of key. If you're starting a new plan, try to get a soil test that's less than 1 year old. And consider the pre-side dress nitrate test, particularly on sites that are receiving manure. Other application concepts or ideas incorporate manure, not only to get the nitrogen volatilization down, but also to get the phosphorus interacting with soil particles where hopefully it will bind and be less likely to wash off the field. Delay manure applications ahead of storms. Volatilization from manure and urea, again, you've got to keep this in mind. That's a big one, particularly on high pH soils. So how do we devise a nitrogen rate? There are actually several ways, and my guess is you will be shown a table, shown a graph, shown a soil productivity index, shown a 5-year running average yield, or be asked to actually calculate one from yield data. So another thing you can do is use an N soil test. There's a number of these out there, including the pre-side dress test. We need to understand the environmental risk for over application, and we're going to pull in economics, weather, crop type, and stage as part of our nitrogen rate. So there's a bunch of stuff out there now. All kinds of entities are trying to predict the sort of the nitrogen cycle flux that happens during a cropping season and try to give you a better concept of how much nitrogen is needed, particularly if coming back in with some sort of side dress. Again, rate considerations, you're looking at all these different things, including leaching potential. Establishing the nitrogen need, there's a couple different ways this can be done. They could show you a maximum return to nitrogen graph, and then you have one number that you're working with. The data that go into this would be your location, the expected price of a bushel of corn, the previous crop, and the price of nitrogen. You may also be asked to sort of calculate a static amount per bushel. In other words, 1 pound of N per expected bushel of corn. Illinois used to be 1.2. Some surrounding states were 1.1. I think Wisconsin might have been as low as 0.8. But anyway, it's a constant amount. And when you do that, you have to take nitrogen credits, including those of soybean. And you also may adjust your strategy with a pre-side dress nitrate test. Here's this maximum return to nitrogen example. And I can't remember if this is corn after corn or corn after soy. Doesn't really matter. I want to get you familiar with the idea that the gross return to nitrogen is the light blue line, and that's always going to be higher than the maximum return to nitrogen. So we get to a certain inflection point where additional nitrogen, the cost of that nitrogen, is not going to be supported by the small increases in yield, and we begin to lose money. So for instance, if you looked at this and started with that concept, you've got 184 pounds of N that you need from a variety of sources. So what would you do? First, you would examine, am I using manure? And you would take credit for that. Or am I using DAP or MAP? And you take the nitrogen credit for that. And only after looking at those two and starter and maybe a surface application pre-plant, it's only then that you would decide how much you wanted to side dress. So you've got to work through that systematically, taking the sources that you know you are having to use, like your manure and your phosphorus source, and taking that away from the total amount. Here is the N need if you're doing this static method of pounds of N per bushel. You take a pound N for every bushel of soybean up to 40, and I think in recent years this has sometimes increased to 50 bushels. So, for instance, if you had 184 pounds of nitrogen needed, and the previous crop had been a 70 bushel soybean crop, with this metric here, you would have credit for 40, and so you subtract that from 184 and get 144 that was needed from other sources. Alfalfa, and Wisconsin's got a lot of good stuff on this. They take 100 pounds of nitrogen the first year in credit and 50 pounds the second year. I've looked high, low, and in between for the yearly availability of manure in terms of the nitrogen amount. And I'm pretty certain on the 50% and 10%, and that would be years 1, 2, and 3, with 25 being the second year. And that one is the one that I've sort of estimated. But the point is, you get nitrogen for 3 years, but the amount diminishes each year. It roughly gets cut in half each successive year, up to 3. Okay? Phosphorus you pretty much take first year, and then potassium first year on the manure. So the timing, the key points, you're going to, again, assess the time of plant uptake and match that as best as possible. You want to look at the mineralization and immobilization potential. And I don't know if this would be on the exam, but a scenario in real life might be you're going corn on corn, you did not do any fall tillage, and you're turning in a bunch of corn stubble ahead of planting. You're going to need some surface applied nitrogen to try to counteract the immobilization that would occur as those bacteria tie up nitrogen as they ingest and send that carbon off as carbon dioxide. Also, weather dynamics, if you know there's rain coming, you're less likely to put nitrogen out on sandy soils if it's going to be a lot of rain. And then also you want to make sure you get planted and you're not waiting for nitrogen application. And this is the reason some people go ahead on the nitrogen. Placement, where are the roots growing? There are some chemical reactions that would lead you to a better practice of banding phosphorus and potassium. So if we have a pH issue that's difficult to solve, particularly high pH or no-till, we may want to consider banding that phosphorus, getting it closer to the seed. Tillage systems, more and more we're seeing evidence that phosphorus, if surface applied in no-till, can wash across the surface in a soluble form or wash into some of the macropores that may have developed with no-till. So it's going to be a good practice to get that banded in down into the soil. Okay, nitrogen timing. Risky soil conditions. Saturated, no, don't do it. Frozen, don't do it. Snow covered, don't do it. This is both for fertilizer and manure. Other things we might want to use, sort of interventions or strategies, urease enzyme inhibitor. Where would you use this? Here be the key areas. And I think I touch on this later in this presentation, but surface applied urea in no-till corn, absolutely, because you've got a lot of urease enzyme associated with that residue on the surface. Manures on surface, yes. If you're injecting or tilling in either urea or manure, there's less need for that urease enzyme inhibitor. Nitrification inhibitors, when you don't want an ammonium source to turn into nitrate prematurely, and of course the fall anhydrous comes to mind on that. We can use some controlled release products. The ESN, so-called Smarten nitrogen, would be an example where you may delay the release of nitrogen and spread that release out over a longer period of time. It's one of several slow-release nitrogen products. So I talked earlier about ammonia volatilization, and here's a look at what that is all about. When you've got that hydroxyl, the OH negative that's associated with high pH, comes in, pulls the hydrogen off ammonium, and the ammonia floats away. So it floats away in high pH soils. Chicken manure in particular has a lot of free ammonia that comes off, and I've had the delightful opportunity as a young man to clean out a poultry confinement area with a bucket loader, and I got so emotional I cried because of the ammonia in my eyes. Okay, coming back to Illinois, here are some things to think about as well on nitrogen losses. Two different forms, and we can extend this more broadly across different soil types. So central and northern Illinois, we have a lot of silt loam soils. In many cases, we have a subsoil that's got decent hydraulic conductivity, which allows us to drain these soils using tile drains. So there's extensive tile drainage under a lot of this land, obviously. Makes them more productive. The soils have a moderate loss potential, but because of these tile drains, we're moving more nitrate out of those soil profiles. In southern Illinois, it's a completely different situation. We typically have more level, poorly drained soils, and the main loss there is going to be denitrification. Okay? So in that case, what's happening is the soil is going back into the atmosphere. It's not leaching because of that tight clay pan that we have below a number of those soils. Here's leaching, primarily sandy soils, soils with good structure. This can happen. Anhydrous that nitrifies in the fall or very early spring before a plant is there to take it up. And we're going to have an excess of water because evaporation is low. The net water movement is down, and that's the form, the nitrate, that gets into tile and groundwater. Denitrification, a multi-step process. You're all familiar with this, but you have to have nitrate, you have to have warm conditions, and you have to have saturation, which excludes oxygen, and then you're going to lose that back into the atmosphere. And that's the main loss mechanism on our flat clay pan soils in southern Illinois. So here is a table that I really want you to wrap your head around. This comes out of that Illinois 590 publication, and you're looking at a matrix here that shows coarse, medium, and fine soil. So coarse would be sandy, medium would be kind of loamy, and some of our very light silt loams, and fine would be silt loams with organic matter, silty clay loams, and so forth. And you look across here, and if you're trying to look at fall application at a temperature greater than 60 degrees, obviously you have a high loss potential no matter what kind of soil you're on. And also look at the first four, basically fall applications and temperatures with and without an inhibitor, different temperatures, and you can see that for coarse soils, it's a high loss potential no matter what you do. So obviously in a scenario, you're not going to want to put a fall application out on a plain field sand with irrigation. So you look through that matrix, the best possible application methods that have a low risk of loss would be a spring application with an inhibitor or a spring split application with side dress on medium and fine soils. So that's obviously the more you split it out, the more you use an inhibitor or go with cooler temperatures in the fall, the better chance you are going to have. So one scenario might be, like I told you before, you might have a farm with a bunch of different soil conditions and you have to treat 50% of all those soils with anhydrous, and you don't want to put it on the sandy soils. Urease enzyme inhibitors, as I mentioned, surface applications, high residue, limited rainfall. The worst thing that can happen to urea would be a light rain to just sort of solubilize it but not soak it right into the soil. All right, let's talk a little bit about phosphorus. Phosphorus, again, you've got to key in on the appropriate soil phosphorus test. Most of Illinois would be Bray. Second choice would be Malick. High pH soils in the western Corn Belt would be Olson. Or you can also use Malick with the colorimetric. So you need to know those soil test extraction methods and where and when to use them. You know there's an environmental risk for over-application. I will tell you that the story of phosphorus has really changed over the course of years. People years ago thought really about the only way you can get phosphorus into water is with overland flow attached to sediment, but we're finding more soluble phosphorus now in our different systems. So take a look at economics, weather, calculating your rate based on your soil test. Okay, so this is a little takeout again, I believe it's from the 590 publication, and they base the manure applications on the U of I phosphorus recommendation for a given field, okay? And this is a little tricky to read through. I'm going to walk you through this. So I've got three scenarios. The amount of manure that you put on is either less than or equal to the amount of phosphorus recommended. It is equal to or up to 150% of that level, or it's over 1.5 times the amount of phosphorus you need. And in all three of those cases, if you drop down below that and you incorporate or inject that manure, that would be in a slurry obviously, greater than 3 inches, you reduce the potential of loss to low in all three of those cases. If you don't incorporate, or your injection is less than 3 inches, so it's 1 or 2 inches, you have a medium chance when you're equal to or less than the P recommendation, and a high chance if you're above that. So obviously, injecting or incorporating manure is going to reduce our loss of phosphorus. So you want to reduce erosion, and you can do this using filter strips, riparian buffers, all the things we know about on erosion control. You can also use basins at the edge of the field. So if, let's say we have some high phosphorus, soluble phosphorus water coming either on runoff or out of a tile system, if this goes into a kind of a stilling basin, and can attach to sediment, that's going to take some of that phosphorus out of the water, okay? So for those of you that get excited or stressed out about tests, I'd like to have you think of yourself walking along a grassy waterway next to the still waters under the bathing light of truth, okay? Hopefully that'll make you feel peaceful. Okay, so all these different erosion controls are all going to help. You also don't want to apply nitrogen, phosphorus in a fall application where you have slopes of 5% or more without some kind of runoff control. Here's again a look at what a phosphorus rate graph might look like that you would try to pull off, and you can see there's a lot of verbiage on there looking at your manure above the critical level. And if you get too high, you actually don't want to put manure on that field at all. Down below on the left side, you might even be able to have manure plus fertilizer. But you may have to look at graphs like this to try to figure out what your starting point is. For instance, if you look here, it looks like at about 60 or 65, the upper manure limit corresponds with that high point of where that graph levels off. Weather and climate are going to be important. Again, look at all your soil characteristics, your crop conditions in determining a phosphorus rate. Take credits for everything, your previous phosphorus application, manure, biosolids, wastewater. I would not be surprised to see a liquid-based scenario. In other words, you're coming in with some sort of wastewater, gallons of wastewater. You might be given an analysis of this. And just, be calm and work through the math. It may have so many pounds per gallon or pounds of P per pounds of water with a conversion factor of weight of water to gallons. There may be a number of different ways that could be approached. This is straight out of the agronomy handbook, and you see that again, we talked about this, but some of the forages and small grains have a much higher phosphorus requirement. And you look at the maintenance range in between there, below the, just a little bit above that critical level. And again, this matrix is shown numerically below with the amount of subsoil phosphorus supply being high, medium, or low. Importance of climate and weather. You want to make sure that you look at the weather forecast if you're applying phosphorus on the surface. We don't want that going out right ahead of a heavy rain, particularly if you're going to come back later and incorporate that. You don't want that on the soil surface. Different mechanisms of phosphorus loss to surface water. Okay, you can lose it over the surface, and I think I talk about this in a later slide, but no-till, it turns out, is actually it's kind of a double-edged sword on environmental concerns. Since no-till, we obviously don't have any tillage, phosphorus is applied directly to the surface, and we could get a highly enriched phosphorus layer right there next to the surface. And that's also where, if we get any runoff, that water is going to go right across there and pick up some soluble P. Of course, we want to have strategies to reduce particulate P loss. That is, be the phosphorus that's riding piggyback on sediment, typically in association with some other cations. So there's different strategies for dissolved phosphorus loss. I read some literature here recently where they're looking at a lot of different things, but they get soluble phosphorus loss in fields that are tiled and then converted to no-till. We have phosphorus coming across the surface and going into macropores down in. One of the possible ways to counteract that people are examining would be to till just above the tile line. So you'd have a little tillage strip, every 100, 200 feet, whatever the spacing might be of your tiles, and that would disrupt the macropores and allow more soil to interact with with phosphorus particles. Okay, yeah, we've looked at this same kind of deal, looking at runoff and leaching. And here's a thing I pulled out of, I think this is out of the IPNI manual, but showing what can happen, what we're looking at for surface runoff, and are we getting infiltration or percolation that could take phosphorus down into the soil, down through the soil, into the tile flow. Okay, same thing again. Another thing you might want to consider is managing the drainage water by putting that through some sort of bioreactor into a stilling basin. Okay, here's the holy grail on your phosphorus risk assessment. So basically, and I know Iowa has an index directly related to manure application. I think I talked about that a little bit in my webinar on calculations. But if you look across here at various parameters or variables that we're looking at, soil erosion, there's a low phosphorus risk potential of getting off site. If the standard practices that you're using result in an estimated soil loss by erosion that's less than the T level, this would be calculated using the revised universal soil loss equation. So let's say a soil you have 3 tons per acre per year is a tolerance. If you're below that, then your phosphorus loss is low. And if you're medium, if it's greater than the tolerance and but somewhat less than 2 times the tolerance, and if you're more than 2 times the tolerance, you've got a high risk. Okay. Connectivity to water. Does the runoff from application enter some place where it quickly becomes surface water? If you're 1,000 feet away, no problem. 1,000 to 200, medium, and if you're closer than 200, this is an issue. So when we start thinking about setbacks for manure, you're going to want to take a close look at that. It says see runoff matrix below. The runoff matrix is basically the different hydrologic classes of soils, A, B, C, and D, with A being sandy that have high infiltration and low runoff. Makes common sense there. You should be able to figure that out. And also your soil test levels. If you're obviously at that high end, if you've got a highly enriched soil that maybe has been over-fertilized or had a lot of manure application over the year, this would be in a high-risk situation. So in general, you would go through and look at kind of the general summary of all of those particular factors to assess your phosphorus risk, your risk of loss potential. Okay, potassium. Potassium they may talk about, but again, you know, my guess would be the main focus is going to be nitrogen and phosphorus. Potassium has no known negative environmental effects that I'm aware of. So, you know, you put out potassium to meet the needs of the crop, adjust the soil test, what have you. You're going to look at, again, the sampling protocol that we looked at earlier, and you're going to look at the clay type involved. There are some clays that are related to micas that actually fix or trap potassium when they go through wetting and drying cycles. Again, straight out of the agronomy handbook, here's an example. In this case, we're going to be looking at the cation exchange capacity of a soil. So if you're on a sandy soil, you can automatically assume that you're on a low CEC. If you're on a dark silt loam, you're going to be at a high CEC. Remember that that little algorithm I shared with you, 0.6 times the percent clay and 2 times the percent organic matter, sum those up. Okay, so we look at this here, and another little caveat that's in the agronomy handbook is if you're on a low CEC soil and need, you want to just take a general approach, you want to do 1.5 times the maintenance amount. I had that in one of the problems I handed out to you last week. So again, looking at the application at planting, there may be something, you don't want this, the seed for salt considerations, particularly if you're using the potassium chloride, which would be the common carrier. Soil sampling between September 30th and May 1. So now we're in that zone that's outside of the late summer and very early fall. You actually would make a downward correction if you had soil samples from that time. Talk a little bit about micronutrients. Micronutrients, again, you know, they're tricky. I want you to remember a few key concepts in terms of where you might be looking to add a micronutrient, particularly maybe in a foliar application in some cases. We're putting zinc in the soil and boron in some cases. Secondaries, I didn't talk much about them, but sulfur can go out. The main thing on the micronutrients is you want to look at the pH levels and the amount of organic matter and give a sense of whether this might be a situation where a micronutrient deficiency is more likely. So we're looking across pH ranges and so forth. I'll show you a little chart here in a second. But basically, most of the micronutrients are more available at low pH. In fact, if you were in Georgia, North Carolina, South Carolina, some of these areas with some native low pH soils, the pH could be so low as to incur or develop manganese toxicities because manganese is so available. So if the pH is right, it's seldom a problem on some of our dark, silty soils, but as you get into more sand, very high yield platform, and in some cases excess organic matter, we can start to see some of these. And foliar applications are a good way to deal with micronutrients in that they're taken up in fairly small amounts, and if you put that micronutrient on the plant, you don't have the soil interference, particularly in a soil pH that's not really readily correctable. Here again are those different charts. You see iron, manganese, molybdenum again is a little bit less available at the lower pH. Boron has a mixed thing, but their main ones of iron and manganese are going to be more available at lower pH. The optimal pH is the reason we typically want our production soil somewhere between 6.2 and 6.8, typically around 6.5. It's going to be acid enough to get micronutrients and neutral enough to solubilize phosphorus. And the only example on that, and that should be a small e, iron, we have lower pH for specialty crops such as blueberries because they have an enormous appetite for iron, so the more iron there is, the better they do, and they're managed at a lower pH. Here are some of the things that can happen with a low pH soil condition. Aluminum toxicity, manganese toxicity, readily available. Keep in mind, aluminum is not an essential plant element, but if it's readily available in solution, it can do damage to roots. If you get into very low pHs, you can slow mineralization, you can slow symbiotic nitrogen fixation associated with our legumes, and again, you get low phosphorus. High pH, we run into iron deficiencies, and there's a kind of a classic scenario with, particularly with soybeans in the western Corn Belt area, and they actually have some soybean varieties that are bred to deal with this iron chlorosis issue, where there's not enough iron getting into the leaves. This can also happen on over-limed soils. So if we have an example of just an over-application, or maybe that small area that's just downwind from a limestone gravel road, those might be some areas where this would show up as well. Manganese and zinc deficiencies, and also you may have low phosphorus. So how much lime do you add? I'm not sure if this is going to be on the exam or not, but basically the idea is you take a water pH measurement, and if this is low, below 6.2 or whatever you're trying to raise it to, what you do, or what the soil test lab does, is they do something called a pH, buffer pH method, okay? So what that is, it's a solution. It's been around for, 60 years or so, maybe more. It's a solution that's pH 7.5, and it's buffered. The term buffered means resistant to change, okay? So if you pour this pH 7.5 liquid in, the acidity in that soil sample will start to take away the buffering of that solution. So if the pH of that buffer pH solution drops down quite a bit, it means that there was a lot of reserve acidity on the cation exchange sites that neutralized that higher pH and buffering capacity. So if that buffer pH hardly changes at all, it means there's very little reserve acidity. Therefore, you need a lower lime rate. So for instance, taking a buffer pH measurement on a sand would likely have little deflection, and you use much less lime than you would to make a correction on a dark soil with lots of clay for going the same distance of pH units. So more organic matter and clay require more lime for making the same pH change. Now, I always used to ask this question in my soils class. You got a plain field sand with 0.5% organic matter at pH 6, you want to go to 6.5. You have a drummer silty clay loam, organic matter 5%, you want to go to 6.5, which requires more lime, and it's always going to be the soil with more cation exchange capacity. So we can lime acid soils, and the reaction on that, we're using the calcium and magnesium to displace hydrogen off the exchange sites where it's neutralized by an anion, either carbonate, hydroxyl, or oxide. And high pH soils are much more difficult to correct because typically they're associated with what's called free calcium carbonate. So they may have calcium carbonate or limestone nodules actually in the soil or in the subsoil. And we have some soils in Illinois called Harpster that are old glacial ponds that were at the foot of some of these moraines or glaciers that had snails and little crustaceans for centuries, and those are still there today, and it's a source of calcium carbonate that keeps those soils with a high pH. Be careful not to overlime low CEC soils. That's a classic. We don't have it as much in Illinois because we don't have as many low CEC soils, but I know that a good friend of mine is a director of Department of Ag in North Carolina. They have that issue all the time where it calls for a low lime rate. People say, I'll just put on 3 times as much and not come back as quickly, and that ends up giving them a high pH because of the low buffered soils. All right, manure. Manure is going to be, I think, on there. In the first webinar, I talked about kind of a step-by-step approach where you may be given some constants. In other words, you have X number of head of steers or, birds, poultry, turkeys, chicken, whatever, and you're given an output from each one of those individual animals. You sum it over a year, and then you start looking at how much you have to deal with, how much land you need. This is kind of an involved approach that you may want to kind of hone your skills on before you go into this exam. Take total number of animals in the unit. You look at the amount of waste that you're getting out of that. You oftentimes will be given a manure analysis. And you also want to take a look at the loss of nitrogen over time if this is stored. And I have one of those examples again in my first webinar. But a lot of times if this sits around, you might lose 35% of the nitrogen in a year. So that's something to keep in mind as we look at that moving end content in manure. So you shall not exceed the nitrogen requirement, and also, you take a look and you get into the higher phosphorus stuff, you have to look at that too. So you basically don't want to exceed either the nitrogen or phosphorus amounts. You do not apply to frozen snow or saturated or flood risk. So we want to keep manure out of those floodplain and bottomland type areas. And we already looked at that risk potential in an earlier slide. So you may have to actually determine the adequacy of your land base. Do you have enough acres with the right characteristics to take that manure? And some of these fields may be out. They may be out because of a setback issue or an extremely high phosphorus type level. Okay, so again, folks, scenario-based, think scenario. A lot of these issues we talked about, I'm telling you, if I think of any more key issues that might be nuggets that would work, I'll try to get those together and get them in an email out to you. But no-till corn, high residue, you see something like that, you're automatically thinking if you're coming in with urea, you want to inject it or get a urease enzyme inhibitor with it. If it's high residue that's plowed down ahead of planting and you're coming back with corn, or you're coming back behind wheat or corn, you've got immobilization issues. Just think of these things. Frozen snow, stay off those. Dealing with your corn stalks, when and where to put manure, phosphorus, all nitrogen, all these different things are going to be scenarios that you may deal with. Here is what I know about the test. Again, just talking to a couple folks with knowledge of this thing. It's written from the performance objectives. Okay, you've got about 50 multiple choice questions, but it's all scenarios. And you're going to have to be comfortable working off of graphs and charts to get some of this information. And there may be some conversion factors that you have to do. They may ask you to go from elemental P and K to P2O5 and K2O, or the other way. Again, this is in the sheet that I sent out, so you can look at that. Might have to go from kilograms per hectare to pounds per acre and vice versa. No manure, figure it out. If you're a person who says, I don't know crap, well, you better start thinking about it. What happens when manure sits? Again, this aging process where the content of nitrogen tends to dissipate. Phosphorus, not as fast. Phosphorus, you only lose about 5% in that first year of sitting. Use manure first, and then if you need additional N after you've taken account of manure, previous legumes, applications of phosphorus, fertilizers that contain nitrogen, that is when you come in with the additional nitrogen. And you may have to select which fields that you're given are best for manure application. Volatilization from urea and manure, think about that with pH, think about slope for application of some of these materials. Phosphorus on sloping no-till is no good, same with manure. Think about P-loss through tiles. You may want to use some tillage in your tilled fields. There's less of a chance of that phosphorus getting into macropores and going out that way. Soil test data for yield goals and looked at effects of rain and temperature on manure mineralization. Let me expand that point briefly. Basically, manure is going to mineralize or release nitrogen faster the further south in the United States it is because of temperature, and the further east in the United States because of rainfall. So these processes of release of nitrogen from really any residue, but manure and biosolids is going to be quicker the warmer the temperature and the more moist the soil is. So that's something you may want to remember as well. Folks, that's what I have for you. Oh, look at that. It came in exactly at 11. Wonderful. So thanks to all of you for your attention, and I think that Dan may jump in with a few questions at this time. I wish you all the best of luck on the exam.
Bill, can you hear me?
Yes, sir.
Okay, I'm back off mute. Dan Davidson. Go through some questions. All right, there's some questions here. Let me pull up a couple files here that came in. Hold on here a second. I want to go back, Bill, a couple on the P loss to tile. That one of the last comments you mentioned. Just a question about kind of reconciling how we're all taught that phosphorus is immobile in the soil.
Right.
So it stays where you put it. Yet how does it get down to the tile lines, get down and go out through the tile lines, and is that a major concern?
Good question. Yeah, this is kind of, again, this is a fairly new revelation or development where, and you know, honesty compels me to report that I'm 61. So when I first learned about phosphorus back in the day, yeah, we thought if phosphorus hits the soil, it's fixed and nothing's going to happen. The only way you'd lose phosphorus would be if particles went off. What they're finding, particularly in Ohio, Michigan, areas around Lake Erie, perhaps Indiana, some of those areas, they started to see soluble phosphorus showing up in tile lines. And as near as people can figure, what's happening is in no-till, there's such a concentrated band of phosphorus to the surface that water moving even slightly across that then gets connected with a wormhole. It basically goes down through that macropore without interacting with a lot of soil particles. So we are, in fact, measuring soluble phosphorus.
So there are those channels, those wormholes, those macropores that exist in the soil,
right? And
you can actually get P to move down to the tile line.
Yep. Yep. So one practice they're considering, and this hasn't made it to the 590 literature, would be to do a little tillage band above the tile lines so that that disrupts the macropores. So if phosphorus-laden water contacts soil or is mixed with soil, it's going to fix that phosphorus, and you're not going to have a problem to keep that soil particle in the field.
Okay. Move on. I have a question about it's very similar type question. Impact of tillage on a fader phosphorus.
Yep.
So you do tillage, you increase the risk of soil loss.
Yep.
But at the same time, you're incorporating the phosphorus into the soil, so you should be decreasing the risk of phosphorus loss.
Yep. Right.
Yeah.
So
how does one reconcile that?
Yeah, that's a good one. And really, the way I like to think about it is as follows. If you have no-till on a slope, it'd be a good idea to potentially band that phosphorus, okay? Then you're putting it, you're disrupting a very, very small amount of soil, but you're allowing that phosphorus to stay in that tight band, and if it moves out from that, it's going to interact with soil as well. If you've got flat, black, drained land, you're better off to till that phosphorus in, and then you're going to have reduced erosion because it is flat. So you use your erosion control methods, including structures. If you're on a side slope, contouring, terraces, that sort of thing, you basically want to keep any soil from moving out of the field. But in no-till, if you get movement through those macropores, you can get some soluble loss.
Really, in that case, it's really, of course, depending where your slope is at and everything like that, is just to avoid tillage, but try to band it in to get it off the surface. Yep. to keep it from running off.
Yep. And then if you band it in no-till, you don't have that enriched zone of phosphorus all across the field if you just surface apply it.
Right.
Yep.
So we're talking a little bit about manure here. So with manure, when you look at NP and K, when you do your manure analysis, and you take all the P and K in the first year With nitrogen, you take it over 3 years?
Yeah, yep, that's the approach. And so if you get into the 590 thing, I think there's a little link that you can go to and look at manure stuff more carefully. But yeah, from all I've seen, it's like a 50, 25, 10 in terms of percent availability each year.
And then on the P and K, you account for about 100% of that in the first year.
Yeah, the literature I read, and I indicated that in that other webinar, I believe, is that phosphorus is about it's about 95% if it sits in a pile for a year. But yeah, you take all the phosphorus and definitely all the potassium in the first year.
Okay. Question. I was under the impression that under the NL nutrient loss reduction strategy in Illinois that it was no longer permitted to apply ammonia even with a nitrification inhibitor above 50 degrees Fahrenheit. Your presentation is using 60 degrees. Am I incorrect in my interpretation of the nutrient loss reduction strategy?
No, I think that the below 50 is definitely the better practice, but the still stuff in the 590 plan has that 60 degree. But you'll also note in Illinois that there are drop dead times, before which you cannot knife in and hide. If it's me, I'm always going to recommend 50 degrees Fahrenheit with inhibitor. I think that's the way to go. That is the best practice.
Can you go back to that slide, Bill, the one where you had all the soil types and those rules of when you use the ammonia and nitrification inhibitor? Can you go back to that slide?
Yeah, I'm going for it right now. Let's see. Here we go.
There you go.
Yeah, that's straight out of that 590.
So the one question here is, that's listed here, fall if your soil temperature is below 50 with an inhibitor, how would that come out across on this table, coarse, medium, and fine? That's not in there. Fall with an inhibitor below 50.
Oh, yeah,
that's like a missing row.
Yeah, it probably is. Again, I snipped this out of that. But if you're talking about, let's see, fall below 50 with an inhibitor would probably lower that across that particular zone. You're right.
So coarse would be, how would that come out? Coarse, medium, and fine. That's the question.
Well, yeah, coarse is sandy soils, up to probably sandy.
Would that be a high risk, though?
Yeah. You want to stay off coarse soils with a fall application.
So that would be high. And for a medium soil?
Below 50 with an inhibitor, it's probably, medium low and medium low for medium and fine would be my guess.
And then for the fines?
Yeah. So it's a continuum. Yeah, obviously, the colder it gets, the better off you are. Using an inhibitor, the better off you are. Delaying till spring is even better. And having some spring with a side dress is the best. That's the way this really breaks out.
Okay.
Yep.
Next question. Are you aware if someone in the last 10 years has developed better lab methodologies to measure available NPK, which I assume is something better than just exchangeable?
Good question. All these soil tests, it's kind of makes people feel sad when they learn about the fact that they're just kind of a relative measure that shows when you might or might not get a response to fertilizer. So I know that there's been some stuff around. People have fiddled around with trying to predict mineralization of nitrogen with mixed success, I would say. There are people that try to measure, the nitrogen that's in the soil profile. And a word about that, by the way, the test works better, any kind of pre-side dress test or whatever, works better the drier the climate you're in. So as you go west in the Corn Belt, it has more application than east in the Corn Belt because of the potentially rapidly changing moisture conditions that exist in a more humid environment, where all changes can occur with nitrogen. So, yeah, there's always room for someone to develop an incredible test that's just dead on. I know that some people spend entire careers working on phosphorus and when to sample and how to test and how this correlates, or also for potassium. So it's all, yeah, I'm not aware of any breakthroughs at this time.
What is the next question? What is the science-based knowledge using or supplementing NPK and micronutrients during critical growth stages of the main crops? I assume you're talking about corn, soybeans, and wheat. What is the science-based knowledge about using or supplementing NPK and micronutrients during the growth period, during when the crop is growing?
Well, you know, there's a lot of people doing work. You know, it's primarily in the nitrogen world that this timing thing is much more critical. Because in general, like I'll tell you too, one of the management practices on potassium is, if you have a very sandy soil, to try to get that closer to planting instead of fall, because there is a minimal but perhaps measurable amount of leaching that can occur if you get a lot of water on those sands. But it's nitrogen, and yeah, there are all kinds of experiments going on to try to demonstrate getting the nitrogen on at a time when the uptake is coordinated. There's also evidence that today's hybrids tend to take up nitrogen a little bit longer than did the hybrids 25 years ago, and may have some increased nitrogen use efficiency. So the timing, it really depends on the year. In other words, if you get a situation where you have perfect rainfall, let's say you put your entire nitrogen out at planting. You have perfect rainfall that continues to pump the mineralization and nitrification of the soil organic matter. You never have leaching. You never have any denitrification. You basically have no loss pathway so that nitrogen's always there. Then that will do as well or better as a split application. The splitting is really ensuring against some event taking away that nitrogen. The downside is, and I've seen some fields where people put out no pre-plant nitrogen, and we're doing, you know, pretty heavy side dress with corn that was like V3 and yellow, or yellow. So that's the trade-off.
Well, that question was a very interesting question, because as you answered it, I'm just sitting there dwelling at about, you know, supplementing nutrients during the growth stages of the crop. That's a very interesting question, because there's a lot of nutrients we're talking about here, like 13 of them, right? And how does this all apply? And they're all a little bit different. So I want to go back to this. Go ahead.
You have to think too about the source and what form the nutrient is in the soil. For instance, sulfur either comes in as the sulfate form, or it can be readily oxidized to sulfate, and that can move just like nitrate. So you know, that's one that is going to be affected by the amount of water that's moving through that soil profile.
What is that value you talked about? 9 pounds. Is it 9 pounds of phosphorus to increase the soil test level? 1 part per million, or 1 pound?
1 pound. So it's pounds of P2O5 to 9 pounds to increase the soil test 1 pound too. So
1 pound.
Yeah,
okay.
But that's split over 4 years, and I've got an example of that problem in my handout that I gave for the last webinar.
Right.
Yeah.
Then you talked about, were they asked what the static N rate is per bushel for corn? You talked about that static rate. Were they asked for a particular number? And, you know, states may vary.
Yeah. I asked someone who's involved with this testing how that works. And I think, don't hold me to this, but I think they're going to have to supply you with something, because there are different approaches depending what state you're in. And this is a multi-state thing. So I would think they'd either have to give you a static amount, or give you a table, or, you know, give you a maximum return to nitrogen graph or something to show what the rate might be.
Yes, they'll probably have to provide those specific numbers.
Yeah.
Okay, how do the sample questions in the IP&I manual compare to the questions on the exam?
Wish I knew the answer to that. I don't know, but I think I looked over that manual, and, you know, I think it's good for the cause. I think anytime you're looking at scenarios and get your mind to think like that, and there's a number of those in there, that's the way to go.
Can you provide the copy of the slides to Thorsten Ulrich or Lisa, and she can send those out?
Possibly. Yeah, we can talk about that.
I mean, we could, just send them out as a PDF file. There's just one question: can you get a copy of the slides emailed to us? Because you have a lot of basic information in there that's good review. So somebody asked that question, if you could provide those. So if you want to do so, we can take that offline though, and see how that works. So
yeah, and they can contact me directly too if they'd like. The person can.
If you have, I'll suggest this, Bill. At this moment, I'm going to ask you a question. Why don't you put on your last slide? Do they have your email address?
I don't have it on this webinar, but I can just tell everybody. I have an imaginary first name that starts with F, so my email is F, as in fearless, Simmons, Simmons, at illinois.edu. And I know, I know a number of the folks out there that, if you want to reach out, if you got a question that comes up, and you want to email it to me, I'll try to work with you.
So let's leave it at that. If they want a copy, if they'd like to request a copy of your slide deck as a PDF, they can just reach out to you directly, if that's okay with you.
That's fine.
Okay. Another question: in manure, is it all the ammonia and nitrogen available in the first year and in manure, is it the ammonia and nitrogen available in the first year and 1/2 the organic nitrogen available in the first year? 25% the second, 10% the third. You talked about that last Thursday. Can you go over that again?
Yeah, and I'm going to. I need to revisit that and look that over, because people ask a lot of questions about that. But there was actually there was another webinar that the American Society of Agronomy put out that covers that. I don't know if maybe too late for these guys to get that or purchase it or whatever, but I think that I heard somebody talked about manure on that and in some of the calculations that you go through. But the thing is, when I teach about manure, the values are all over the place, and so you really have to pay attention to what the characteristics are that they tell you in these particular problems. And yes, there is availability later. It's the organic portion of that nitrogen mineralizing over time. And so we're putting out ammonium and nitrate depending on the conditions for mineralization and nitrification.
Okay. A question here on this. It goes back to, were they ever asking any questions on like stratification of pH, potassium, phosphorus in the soil in a no-till situation, and how one manages that?
Well, I think it'd be fair game, and I think probably, thinking about pulling that concept in and thinking about what it might be paired with. For instance, and I wouldn't worry so much about the K, from a water quality standpoint, obviously, but if you have stratification of phosphorus in the top and you have any slope at all, you have a potential environmental issue there. The agronomic part of it, again, I'd at least have my mind open to the potential of banding phosphorus in no-till for a couple of different reasons there. Primarily to get it in the root zone, which is stressed in 590, and also to get it out of the way of any kind of environmental loss off-site.
Okay. I think this comes to pretty much the end of the questions. One of the questions were that both these webinars remain on the ILSOI website. Dr. Simmons' webinar last Thursday was up by the end of day Friday. This webinar today will be up tomorrow, and they will remain on the ILSOI website for some time. We'll make sure that come the August exam, these two webinars plus the recording of Dr. Simmons' presentation will also be online next summer prior to the August exam. Just a comment here that the exam is on Friday at 1 p.m. at the Illinois Department of Ag offices in Springfield. The exam starts at 1. You can check in at 12:30 p.m. First I want to thank Dr. Simmons for taking his time today and last Thursday to present these two webinars in preparation for our exam on Friday. And Dr. Simmons, thank you very much for your time and presentation. They were very good. As Dr. Simmons said, he gave his email address, and you're welcome to reach out to him with a question. If you'd like to get a copy of his presentation, he can forward that to you. So just reach out to him directly. If you registered for the event today, you will get a CEU probably for about an hour and a half now for 1.5 CEUs when we close down. And if you listen to the recording, then you can self-apply for the CEU on the National CCA website. On behalf of the Illinois Soybean Association, thank you very much for listening in today on this webinar and the one last Thursday. And I guess I can wish you well when you take the 4-hour exam on Friday. Thank you much for your attention.